Ever looked at a Bitcoin address and noticed it starts with the number 3? It seems like such a tiny detail, but it actually tells the story of a massive leap forward for Bitcoin. So let's unravel that story, shall we?
Right, so if you've been in the Bitcoin space for a while, you've seen them all. Addresses that start with a 1, the newer ones that start with BC1, and of course, these ones, starting with a 3. So what's the deal? Well, that 3 is anything but random. It's actually a signpost pointing to a really brilliant solution to a huge problem. And, as we're about to find out, a hidden flaw that took years for us to fully wrap our heads around.
Okay, so before we can really appreciate just how clever this solution was, we gotta rewind. We need to go back to the early days and understand the problem it was built to solve. See, back then, Bitcoin was powerful, no doubt, but for some things, it was just clunky, really clunky. So imagine you wanted to do something a little more complex with your Bitcoin. Like maybe you needed 2 out of 3 of your business partners to sign off before any money could be spent. Well, those rules, they're called a script, had to be jammed right into the transaction itself. And these scripts could get gigantic. We're talking thousands of bytes long. This created a couple of major headaches. First, the person sending you the money had to pay a way higher fee because the transaction was so bloated. And second, you had to somehow give them this enormous complicated script every single time. It was just super inefficient and way too expensive. So Bitcoin's developers really needed a better way to handle these complex rules without making every transaction huge and costly. And they found their answer in one of the most powerful tools in all of cryptography, the hash. And the solution they came up with, all the way back in 2012, was called Pay-to-Script Hash, or P2SH for short. Now, the core idea here is pure genius. Instead of making the sender deal with your big, messy, complicated script, P2SH lets them pay to a tiny, simple fingerprint of that script, a hash. The actual complex rules, they only get revealed later on when you go to spend the funds. It's a brilliant way of just kicking the complexity down the road. A good way to think about it is with a locked box. Let's say you've got this treasure chest with a super complicated, custom-made lock on it. That's your spending script. Now, instead of mailing that entire, heavy, complex lock to someone who wants to put treasure inside, you just give them a short, unique serial number for it. That's the hash. They lock the chest using just that simple serial number. Then, later, when you want to open it, you show up with the actual, physical lock to prove it's the right one. And only then do you use your key. P2SH is exactly that. You pay to the serial number, but you spend with the original lock. All right, so that's the big picture. Now let's pop the hood and take a look at the simple but incredibly rigid formula that makes this whole thing tick. This right here is what every P2SH transaction looks like to the Bitcoin network. It's a super strict 3-part command. OP hash 160 tells Bitcoin, get ready to hash something. Then you have the 20-byte hash. That's the serial number from our locked box analogy. And finally, OP equals says, okay, now take the real script the spender is providing, hash it, and check if it perfectly equals the hash I just gave you. If it matches, the funds can be spent. If not, no deal. Simple, clean, and always the same small size. And when I say this template is strict, I mean it is absolutely rigid. As the source material warns us, this is not a suggestion. If you mess with this format in any way, if you add one extra command, get anything wrong, the whole thing just falls apart. Best case scenario, your Bitcoins are unspendable, lost forever. Worst case, they could be spendable by literally anyone. So yeah, precision is everything here. And this is how we finally get back to our original question about that number 3. So to create the address that you actually give to people, that fingerprint, the hash of your script, gets encoded. And during that encoding process, a special version number is tacked onto the front, the number 5, to tell the network, hey, this is a P2SH address. And when you run that whole thing through Bitcoin's standard address making process, what pops out is always an address that starts with a 3. So that's the big secret. A 3 address is just a sign that says you're not paying a person, you're paying a puzzle.
Now, P2SH was a fantastic innovation, a real game changer. It's what made things like multi-signature wallets common and easy to use. But as time went on and computers got faster and faster, cryptographers started to realize that this elegant solution had a tiny theoretical crack in its foundation.
Okay, to get this flaw, we need to quickly talk about 2 ways to attack a hash. First, there's a pre-image attack. This is like I give you a lock, and you have to find the one and only key in the universe that opens it.
With the hashing algorithm used here, that's pretty much impossible. We're talking a 1 in 2 to the 160th power chance. But then there's a collision attack. This is different. This is like finding any other key, a totally different key that just happens to open that same lock. And it turns out, finding a collision is way, way easier. It drops the security level from an impossible 160 bits all the way down to a much more thinkable 80 bits. So how big of a deal is 80-bit security? I mean, 2 to the power of 80 is still a ridiculously huge number. But in the world of high-powered, specialized computing, it's not out of the question. To put this in perspective for you, 2 to the 80th is roughly the number of hashes the entire global Bitcoin mining network can crank out in just 1 hour. Now, they're using different hardware, but it just goes to show you that a well-funded attacker could theoretically pull this off.
Now, for contrast, let's look at the security of modern Bitcoin addresses. They have at least 128-bit collision resistance. If you told that same unbelievably powerful Bitcoin network to try and crack one of those, it would take them about 32 billion years. The difference is just staggering. 80-bit is on the edge of feasible. 128-bit is just cosmic. And that's exactly why the standards had to evolve. So while nobody's 3-dress funds were suddenly stolen overnight, the writing was on the wall. P2SH did its job beautifully. It was a crucial step, but it was time for Bitcoin to level up to even more secure standards. This table really lays it all out, doesn't it? Our P2SH3 address has that theoretical 80-bit collision risk we've been talking about, which is why, today, it's considered legacy tech. Modern addresses, the ones usually starting with BC1, they use stronger hashing algorithms. This pushes that collision risk way past 128-bit, into a realm that is, for all practical purposes, completely negligible. That's why they are the absolute recommended standard for any new wallet you create today. So the takeaway here is pretty clear. P2SH was a game changer, no question about it. It solved a massive problem with script size and cost, and it paved the way for features we absolutely rely on today. But technology just never stands still, right? What was once cutting-edge security is now a legacy system, which has been replaced by stronger, more robust successors that give us all much greater peace of mind. And that leaves us with a pretty fascinating question to think about. P2SH was a vital stepping stone in Bitcoin's journey. It makes you wonder, what technology that we all use today, the stuff we consider perfectly good enough and secure, will we be looking back on in 10 years as the legacy system of tomorrow?